All right, hello there, guys. So what we're going to be doing in this video is the two-tank problem. So for this problem, what we have is we have two tanks of different sizes, spherical tanks, connected at the bottom, where this tank has one inlet adding fluid. This tank will have one inlet adding fluid and one inlet exiting the tank, allowing for fluid to leak. So what we're trying to find first is how does the height of these liquids change? So from our initial height here to some final height. So first things first, we have to assign variables and labels to everything. So for this one, we're going to say Q1 for the flow rate into tank 1, Q2 for the flow rate from outside to inside of tank 2, Q12 for the fluid traveling from tank 1 to tank 2, and then Q3 for the fluid leaving this tank. So first equation we can set up is our change in volume with respect to time. So as time goes on, this inlet will add fluid while this outlet will take away fluid. So over time, our change in the volume will be reliant on the difference between these two. Now for tank 2, it has two inlets, Q2, which will put fluid in, Q12, which takes fluid from tank 1 into tank 2, but the outlet, Q3, is removing that fluid. So our equation looks like this, Q2 plus Q12 minus Q3. So we have our first two equations to solve. Let's get this out here. But what you'll notice is Q12 and Q3 depend on the height of the fluid inside. Because remember, with tubes and fluid going across them, we have one pressure and one velocity this way, and then the exit pressure and then the exit velocity. So for example, with our first tank, P1 and V1, now the fluid will start at rest here, so this will be 0. So if it starts at rest with P1 here, it goes through, and there's going to be a P2 and there's a V2, or velocity 2. So now we have to look at how the energy changes through this tube. So the change in energy is equal to pressure over density plus Gz plus velocity squared over 2. Now, since no energy is lost or gained during this transfer, it'll be 0. So pressure from the outlet, P2, pressure from the inlet, P1, over density. Keep in mind they're the same fluid, so they have the same density. The Z of both liquids are the same because liquid on this side is from the top to the bottom of the pipe, and same thing on the outlet, from the top to the bottom of the pipe. So this will just go to 0. So we're left with V2 squared minus V1 squared over 2 equal to 0. And keep in mind, we said V1 is already at 0 because this fluid right here is at rest. Well, not at rest, but the difference will just be V2. So with that, our equation becomes P2 minus P1 over density plus velocity 1, 2 squared over 2 equal to 0. So what happens now is, keep in mind, another way to write pressure is density, gravity, height. So if we plug these in for the corresponding pressures, since densities are the same, density will cancel out. So we are left with G times H2 minus H1 plus 1/2 velocity from 1 to 2 squared equal to 0. We move this to this side, and we get 1/2 velocity from 1 to 2 squared is equal to G times H1 minus H2. So with that, we take the 2 multiplied by this side and then square root it. And we got our first equation for velocity from 1 to 2 is equal to square root 2G H1 minus H2. Now you may be asking yourself why we found velocity. Scroll down some more real quick. Not what I meant to do. All right, there it goes. But the reason we found velocity is flow rate is equal to the area, or the cross-sectional area of the pipe, multiplied by the velocity of the fluid. So since we have velocity 1, 2, with our area, the cross-sectional area for the pipe for 1, 2, we get Q12 equal to the area of 1, 2 multiplied by its velocity. So what happens here is A12, plug in our equation for V12, 2G H1 minus H2. So now we have our flow rate for Q12, or the pipe of 1, 2. Now we just need to do the same thing for our second pipe. So we have our second tank going to our outside pressure, P3, V3. So same deal as our last one, except this time this will go to 0. And the reason why this will go to 0 is there's no fluid pushing back in here. So there's no pressure exerting on the fluid to push it back this way. All the pressure is going out this way. So our equation same deal, no change in energy, we'll go straight to 0. So pressure negative P2, because remember, outlet minus inlet over density of the fluid plus GZ, just 0. And then, like our last deal, this will go to 0, leaving us with the velocity from 2 to 3 squared over 2. And same deal here, P equal to rho GH. Rho will cancel out. We're left with negative GH2 take it to the other side, multiply by 2, square root it, and we are left with the square root of 2GH2. Now, the reason we're using the height level for the fluids in the spherical tanks, is because these tanks are connected at the bottom down here. So all this fluid up here is pushing down on this single point, giving us that H. So with that, we have our Q23, which is cross-sectional area of pipe 23 multiplied by the velocity. We plug that in, we get A23 multiplied by square root 2GH2. Let's scroll this down more. So now we have our flow rate for both of our pipes. We have this flow rate. Make that a little bigger. We found flow rate for this one and this one. And then these flow rates up here, we have to set. So now we found out the equations for these two. Next up is to figure out what these are for steady state. So remember what steady state means is the change in volume for these two tanks is 0. So for tank 1, we have Q1 minus Q12. So at steady state, the fluid going into the tank must be equal to the fluid going out of the tank. And if we just plug in our equation for flow rate from 1 to 2, we get Q1 is equal to the area of pipe 1, 2, multiplied by the square root of 2 times gravity times H1 minus H2. And now to find Q2, we're going to do the same thing, but this time we are going to do the second tank. So dV2 dt is equal to Q2 plus Q12 minus Q3. So at steady state, Q2 must be equal to Q3 minus Q12. Keep in mind Q3 in this case is the same as Q23. I'm just doing Q3 because it's not going into a different tank. It's just going outside. So what happens now is we have Q2 is equal to area of the pipe 3 times 2GH2 minus cross-sectional area of pipe 1, 2 multiplied by 2GH1 minus H2. So there we have our equations for steady state flow rates for Q1 and Q2. However, our problem doesn't stop here. Now what we got to look at is how each tank's volume changes with its height. So we want to find out what that height is as well. So say after 2 seconds or some really small amount of time, the fluid in tank 1 changes by this amount. And the height of fluid changes by this amount, dH. So if you look at it in a scale or like a graph format, where our x-axis here is h and our y-axis is radius, from the bottom of the tank to the top of the tank, and right here h is equal to 2r. This line is our original, and this line is our final. So the shaded region rotated around the axis is our dV. However, the distance between these 2 points is our dH. However, if you notice, as dH approaches 0, what happens to this rotation is it becomes more and more cylinder-like. So the volume is just equal to the radius. We'll pi the radius squared, the area of the circle, multiplied by dH, mimicking the equation for a cylinder. So what happens now is we need to find out what R is, or well, R in terms of H. So if we look at this tank 1 again, here's our fluid, initially at 5 meters. Here's our radius. The distance from this point to where it meets the sphere is R, while this point line right here is big R, our R in this graph. So to find it, all we need to do is some right-angled Pythagorean theorem. So radius of the sphere, keep wanting to say cylinder, my bad, is equal to big R squared plus, remember this is however many meters from the bottom of the sphere. So what it's going to be is R minus H squared, because the point here, the R here, is the same as if this was down here. That's why this is squared, because if it does come out negative where H is greater than R, it's still going to be positive. If we take it to this side, we get R squared minus R minus H squared is equal to big R squared. So if we FOIL this out, what we get is R squared minus R squared plus 2RH minus H squared is equal to R squared. So, as you notice, the R squareds will cancel out, leaving us with 2RH minus H squared is equal to r squared. Square root both sides, and we are left with 2rh minus h squared is equal to r. So if we go back to our formula, dv equal to pi r squared, so we get 2rh minus h squared dh. So now we have our equation for relating volume to height, or the change in volume to the change in height. So if we look at how volume changes with time, what we can do is take the dt to this side of the equation, giving us dv1 equal to q1 minus q12 dt. 1 second. So with this equation, we can plug in our values for the first tank into this equation, giving us pi 2rh1 minus h1 squared, all this times the change in height 1. So if we take our dt to this side and this expression to the other side, we are left with our change in height with respect to time equal to the difference in the flow rate 1 and flow rate 1,2 over the area, or the dV we calculated. So the pi times 2rh1 minus h squared. So that's our first dH1 dt equation. We're going to go down some more. And then do the same thing for our second tank. We're going to have pi 2r2h2 minus h2 squared dh equals to q2 plus q12 minus q3 dt. Same deal, moving dt to the left side, this expression to the right side. Left dh dt. The change in height in tank 2 with respect to time equal to the flow rate going into tank 2 minus the flow rate going out of tank 2. All of that over the change in volume. All right. Now what I'm going to do now is I'm just going to rewrite the equations we're going to need for our coding, which will be coming up later in this video. So our first equation we did was dv1 dt, which is just q1 minus q12. dv2 dt was q2 plus q12 minus q3. the 2 inlets minus the 1 outlet. Our change in the height for tank 1, specs to time, is Q1 minus Q12 over pi 2 R1 H1 minus H1 squared, or the area, the area multiplied by the height, giving us the volume of the change in tank 1, which is just a cylinder, dH2 dt follows the same spirit of dH1 dt, but it's Q2 plus Q12 minus Q3, all of that over pi 2 R2 H2 minus H2 squared, and then our at steady state equations. So at steady state, remember, dV dt will be equal to 0. So Q1 will equal Q2, and Q12, which is just A12 square root 2G H1 minus H2. Q2 at steady state will equal Q3 minus Q12, which is just A, or the area of pipe 3 going out of tank 2, multiplied by 2G, the height of the fluid in tank 2, subtracted by cross-sectional area of pipe 1, 2 times square root 2G H1 minus H2. All right, so what I'm going to do is I'm going to pause the video, and I'll be right back with Google Collaboratory, and we'll be putting all of these equations in the code, and then finding out how the height and flow rates will change given a certain set of parameters. All right, guys, so I'm back, and we're about to do the coding section, where we're taking the equations we found in the first part of this video and putting it in the code. So our first deal is how we're going to set up our system. Now, what I'm going to do here is I'm going to make our whole system an object. I'm just going to call it a 2-sphere system. So the reason I am doing an object instead of going out and creating variables, like say, for example, A12 is equal to 0.2, R1 is equal to 1.5, and so on, is just because it keeps all the variables together. So, for example, in our init step, for chamber 1, what we have is we have an inlet flow rate, so Q1, equal to some value. We have an outlet flow rate, also equal to some value. And then we have a cross-sectional area for 1, 2, the pipe going from chamber 1 to chamber 2, equal to some value. The sphere of the tank has a certain radius, which we'll call R1. And then chamber 1 will have an initial height. And for chamber 2 now, we are going to have self dot Q2 for the inlet, Q3 for the outlet. We don't need to redefine Q12 because it's up here in chamber 1. It also has a cross-sectional area for the pipe leaving the second tank. Let's call that A3. We'll have an initial height, which we'll call H2I. And then finally, it will have a radius. So now, what you're going to notice is if you remember back in the OneNote notebook, we have equations to solve for Q12 and Q3. So what that means is instead of giving Q12 and Q3 values, what we can do is we can make them functions with respect to time. So need to go up here real quick, and what we're going to do is we're going to import Jack's NumPy. JNP. Because what's going to happen is self.a12 multiplied by jmp.square root of 2 times gravity, which is 9.81, multiplied by the difference in heights. I have this, so let's be H1I minus H2I. I do not know why I put lambda there. I was thinking of something else. My bad. Anyways, so same deal with Q3, except we're going to do area, cross-sectional area of type 3 multiplied by the square root of 2 times 9.81 multiplied by the height in chamber 2. Now what's going to happen here is no matter what we put these values to, because they're all set to 0 right now, these will always go to 0. So what we're going to do, or what I'm going to do, is I'm going to make a method known as steady state. And what's going to happen is when I'm done setting all these values, is I'm going to copy and paste these into here. And what I'm going to do is save myself time and do that. So what's going on here is Q1 is equal to Q12 at steady state. If you remember from our OneNote video, or part of this video, I mean. But Q1 is equal to Q12, which is this equation right here. Q3 is equal to this equation right here. And then define Q2 at steady state. It's going to be self.Q3 minus plus, no, hold on. Yeah, Q3 minus self.Q12. So we have one of the inlets is equal to the outlet minus the other inlet at steady state. So what we're going to do now is we are going to have a method here which handles how this object displays itself in the console. So what's going on here? Now what self.dictionary is right here, this is just where all of your items are kept. So for example, self.q1 is kept in this dictionary. And if I show you real quick and put pass equals two-sphere system sys.dictionary, you're going to notice A12, A3, Q1, Q12, Q2, Q3, R1, R2, H1I, H2I. All of these values here. So what's happening here is our I is iterating through all of these like it's a dictionary. So what we're going to do is our res variable, which we're going to be returning to the console, is going to pick up all of these values, starting with the key, I, tab, equal to tab, the actual value. So to show you what I mean, now instead of doing our dictionary, if we look at just sys, you're going to notice all of our things are currently in one line. Now the reason it's doing that is because I'm dumb and forgot to put the /n. But if you look at it now, you're going to see all of our variables on the left-hand side with their values on the right. So all we have to do now is we're going to set up our system. So our system has initial heights of 5 meters in tank 1 and 3 meters in tank 2. Our system will also have a radius of 4 meters for tank 1 and 2 meters, in tank 2. And then our system will also have a cross-sectional area of type 1, 2, is equal to sys.a3, which is equal to 0.2 meters squared. If we do that, we look at our thing again, you'll notice our values update a little bit. We got 0.2 and A12, 4 and R1, 5, H1I, just as it should. And now if I run the steady state method, fingers crossed, this will get our system to steady state. As you can see, we have 1.25, 1.25, and so on. Now to make it even clearer, what I'm going to do is I'm going to add the change in volumes for each chamber. And then what's going to happen here is when we run steady state, our change in volume for the first tank, if you remember, is just Q1 minus Q12. Our change in volume in the second tank is Q12 plus Q3 minus Q3. That is supposed to be Q2. I promise I can read. All right, so if we rerun that, rerun this, get it a steady state, you notice down here dV1, 0, dV2, 0. So we are at steady state. Now, however, we get into the more complicated part. We need to find out how our system changes in regards to height with respect to time. So if you remember, our dH dt equation was just our change in volume over our equation for the cylinder we found. So for example, I have H1F equal to H0 So the reason I'm doing this is when we plug this in to solve IVP, what's going to happen is our object will save these values, so we can just use our sys command right here. And down here below dv2, we'll have our h1f or h2f, and we'll be able to see our final values of h. So what's going to happen now, where is it at? Right there it is we need to find Q12 again, which is going to be self-dot A12 times JNP dot square root of 2 times gravity times self dot H1F minus self dot H2F. Excuse me. Self dot Q3 is equal to self dot A3 multiplied by the square root of 2 times 9.81 times self dot H2F. Now, when you look at this, you're going to notice that we have a potential negative in the square root. So to fix this, what I'm going to do is I'm going to do JMP.ABS for absolute value. But what we want to do is if H1 is less than H2, this will be negative. And if the first height is lower than the second height, it means the flow, instead of going from 1 to 2, will be going from 2 to 1. So it's going from 2 to 1, we want to reflect it in the value. So this should be negative. So to do that, we're going to do JMP sign, where we're going to plug in our difference equation right there, H1F minus self dot H2F and so if this returns a negative number, it'll multiply the entire equation by -1, but if it's positive, it'll just multiply by +1. And then finally, we can return an array using JMP again to find our DH DTs. So remember, dH1 dt requires Q, but our flow rate going into tank 1 will not be constant throughout the entire problem. It'll vary with time. So before we do that, we need to define two more methods. Or well, probably be easier if I do it up here. So we have self.q1t equal to lambda, or actually, hold on. Let me put it in the steady state method. So self.q1t is equal to lambda, which is just a fancy way of saying function, or variable t. So what we're going to need first is we want to do a sigmoid, where our function is compressed between two values, and when we set up a time for it to switch, it'll go almost instantaneously from the first value to the second value. So let me go back up here, and we are going to need jacks. So we got jacks.nn.sigmoid our t minus our tn, or our time when it switches. For this problem, our inlet will change at 100 seconds. And we're going to keep our scale at 1 for right now. Later on, we'll play around with it, see how changing the scale affects our graphs and our final values. But first, we are going to have our 0.8 times self.q1 minus self.q1. So what's happening here is our sigmoid is basically shifted 100 units to the right. And what this is doing is it is calculating how the difference basically from the new value from the old value. We're going to add that to our old value, because otherwise we'll just be stuck between the negative of this and the positive of this. And then same thing with Q2, lambda t jack.nn.sigmoid t minus 200 this time, because our system will switch at 200 for tank 2. But instead of going down, our inlet to this tank goes up by a factor of 2.5. So we got self Q2 minus self.q2 plus self.q2. So to show you how this works, let me get Plotly in here real quick. Make subplots. Plot, so jmp.linspace. Let's just do values from 0 to 200, where there's a value each second. And go back up here real quick. We need to add graph objects. Add trace go.scatter, our x is equal to t plot, my bad. Now my variable names mixed up today. And our y is going to be sys.q1t tplot dot show name go not defined. Try that again. Oh god, that hurts my eyes. Please give me a second. Plotly.io templates.default equals plot dark. Okay, thank God. So, but as you can see, our initial at steady state is around 1.25. It's a little bit more than that. But as you can see, there is very little decline before the switch. But as soon as the switch occurs, it is almost instantaneously dropped from 1.25 all the way down to just a little over 1. Then if we wanted to check again with Q2, we're going to want to change this. Because remember, for our Q2, our flow rate increases, whereas Q1 will decrease. So same deal here. This shoots up almost instantaneously at 200 seconds from 2.28 all the way up to 0.7. So if we go back to our dHdt now, if you remember, our dH1 dt is going to be our self.q1t at, give me a second to think, t minus self.q12 and then all of this is divided by pi times our radius from the surface of the fluid. So our radius from the surface of the fluid squared, I should say. Pi times, what was it, 2 times our R1 times our H1 minus our H1 squared. Then same thing with dH2 dt. Over pi self dot R2 self dot H2F minus self dot H2F That gives us our equation for dH dt. And now finally, we just need a method for something called solve with a Tn value, where we're just going to solve the IVP that goes along with dH dt. So to do that, we need to come back up here and get the solve IVP from SciPy. Great. Import solve IVP. So what happens here is we're going to have a variable called res, which is going to be equal to solve IVP. Our function is going to be our DHTT method. Our T span is going to be 0 to T end. Our Y naughts are going to be a tuple with the initial height 1 and the initial height 2. And we're going to turn on dense output. And then what we're going to return here is the sol, which is a generator object, which happens when you use the solve IVP. Or it's going to be a generator attribute, I should say. So we run that, get this to steady state, and then solve it. With our Tn, so we're going to have a switch occur at 100 and 200 seconds. So if we set to 300 seconds, we should see how both of them affect the height. I am having a roll today. All right, so that ran. Let me go down here. And if we take a look at res, all right, so as you can see, what happens is as we plug in a time, what this will give us is the heights of tank 1 and tank 2. So if we plug in, let me make this from 0 to 300, 301, just like how we have our Tn here at 300. And there's a graphic if you want to look at it, but if we go down here and plug in our T-plot, what you're going to notice is our height starts at 5 and almost pretty much stays there until it spikes down to around 4.5. And then towards the end, it dips back up just a little bit. And then same deal with our second tank, where 3 keeps going. Then there's a little bit of dip right in this area. But then you notice it goes up extremely fast towards the end here. So if we go up here, and what we're going to do is we are going to get rid of this for a second. Do fig that add scatter. add trace, go dot scatter. Our x is going to be equal to t plot. Our y going to be equal to res 0. No, our res t plot 0. Then we're going to call this function. Why is there another? And get that bracket out of here. We're going to call this line h1. And do row 1, column equal 1. Got a comma there. We're going to do fig add trace go dot scatter t plot y equals plot 1. I'm going to call this one h2. We'll put it on the same graph as our h1. And then if we run this command, what you're going to notice is right around here at 100 seconds, you see this dip occur. So right after we turned our inlet pipe down, our H1 started decreasing. And then same deal here, it started decreasing because more fluid was leaving the system through the outlet pipe than it was coming in through the inlet pipes. However, as you see right around here at 200, we have a huge jump in height and a gradual jump here, because with Q2 going in, what's happening now is instead of fluid going from tank 1 to tank 2, fluid will now be going from tank 2 to tank 1 because more fluid is getting pushed through tank 2. So let me edit this code a bit real quick. What we're going to be doing here is we're going to be making our subplot have multiple graphs on it, so we can look how the flow rate changes and then how the, that's what I'm trying to say, how the flow rate changes versus how the height changes. So to do that, let me make it more rows than columns. Fig dot add trace dot scatter t plot y equal to sys dot q1t t plot, and we're going to name this one Q1. I'm going to put this on the second row, first column, and then we're also going to add Q2 onto that same graph. Go dot scatter x equals t plot y equals this dot q2t t plot, and we are going to name this Q2 on row 2, column 1. So if we run this, as you can see, our Q1 dips right at this 100-second mark. And then our Q2 spikes at that 200-second mark, showing us why these take a dip and why this one increases. So if we look at our system one more time, after our 300 seconds, just ignore the Q1T, Q2T real quick. you see our final heights of 4.62 or 63 if you want to round it, and 3.48, which are just these very last dots right here. All right, now most of these are correct, these values, except Q1 did not update, Q12 did, Q2 did not update, Q3 did. We have our initial height still here. So what we need to do is go back and update the code so that Q1 updates, and as well as Q2, and so do the DVs, because currently the DV is not at steady, the system is not at steady state anymore. So DV is pretty simple. All we need to do is go self dv1 equal to self q1 minus self dot q12 self dot dv2 equal to self dot q12 q2 plus self dot q12 minus self dot q3. Now before that, we need to update our q1 values, so self dot q1 to self dot q1t at our tn value, our self dot q2 be equal to self dot q2t tn. All right, so if you run this again, run this. Ooh, what did I do? What did I do? Oh, okay. Okay. So what's going on here is Jack does not like integers. I think this is what's happening. So if I do this again, sweet, I did it. All right. Okay, I'm gonna have to fix that too in a second. Let me see what Sis is saying. Okay, so so Q1 is correct on here, but it's not correct in the graph. And same thing with Q2 is correct on here, but not in the graph. But we have our dv1 and our dv2 now. We still need to get rid of these two. So let me go back and look and see what's causing that to happen. So if I sys q1t at 300, okay. Let me look at the dictionary, see if anything's weird's going on there real quick. Okay, so what's going on is they are starting out at the values they should be ending. Let me read through this one more time. Let's see. Let me try running all of it one more time. It's still being funky. Okay. Let me try commenting these two. Let me try commenting these out again. And see if it's a problem with the two functions, or the two methods. Okay, so whatever's going on, it's happening in this Q1T, Q2T function right here. So what's going on is Q1 is getting redefined here. So like the initial, that's why, okay. Okay, I think I know what's going on now. So what I'm going to do is be self Q1T T plot in here, and space 0 T end int T end. Excuse me. So what we're going to do is flow rates equal to a tuple self 1T T plot 2T T. So when this runs, it'll have the initial steady state values, but when this runs, it'll adjust the Q1 and Q2 values to the final values. So if I return this along with the sol generator, flow 0 flow 1 run selected cells. All right, now it's working. Okay. Gave me a mini heart attack there. All right, gonna go back to our sys thing, Bob. And we have Q1, which is correct with our graph. Got Q12, A12, still the same. Got all our values. Now all I'm gonna do is just take out these two and we'll be done. So here, Fi Q1T. All right, so there's going to be our last set of values. Here's our graph if you want to look at it again. But yeah, with that, I'm going to go ahead and end this video here. All we did was we solved our spherical system. First, in our OneNote, we started out with our steady state values. And with that, we solved the IDP using SciPy. Got all our final values, so you can display it here. And we got all our values over time using Plotly and this. Now, I kind of lied. Before we end this, let's look at how the scale affects our sigmoid functions. So, to add a scale to these, all we got to do is divide this by that scale. So initially we had 1, so you wanted a scale of 0.5 for both of these. Oops, got a divide sign. All right, and as you can see, our little switches got a little smaller. So say we wanted to get that even smaller. Where is it at? Say like 0.01. See, now it's a full-on corner. It goes straight there. So the smaller we make that scale, the quicker the jump is. But now that we sort of discussed that, I really am going to end this video. You're going to find a couple links down in the description below. There's going to be labels for them. One is going to be for a Google Doc talking about this code. And then another is going to be a link to the OneNote notebook you saw earlier. I'm also going to leave a link to this script if you're going to play around with it. But other than that, I will see you guys around. Have a nice day.